Hello, hello. I decided to stream briefly this evening. Since last time I decided to spend 10 seconds on OBS and make going live, be right back, and the main scene. Yay. This evening I thought writing the DHCP and DNS server would be kind of cool, but less interesting than... But those two would be a lot less interesting than connecting an ext4 file system exposed as a network block device from the host. This is one of the... This capability I added to old TinyRange relatively recently, but it's been incredibly successful. What it means is that TinyRange keeps a in-memory representation of an ext4 file system that the virtual machine will mount as its root file system, and TinyRange can write to that file system, do whatever it likes with it, and the virtual machine, once it's started up, completely takes it over. It just works like normal in the Linux kernel. So it means that the host can add files to it. The guest can then use it. Big benefit of this, it's super resource efficient. It's low memory consumption. It's copy on write. So whenever you make changes to it, those changes stay in memory. So it's extremely efficient. It's got a low performance overhead, and it's completely cross-platform, because we are going to be implementing, hopefully in just this stream, but maybe later streams as well, I suspect, support for creating an ext4 file system that's fully valid, that we can entirely test in pure Golang. Let's get started. So, let's see if I have clock installed. I do. So as you can see, right now we have about 981 lines of code. That number is going to go up by a lot, since there is a number of different features that we will need to add for this. So let's start creating directories. So we will have a file system, we will have an ext4 directory, we will have a VM directory. So I'll be going through the internals of this as much as I can, but it's honestly a lot of code. So I'm just going to start by pasting in the basics of this. The first one is a little bit of generated code that I have. I will add the tool to the repository of how we generate this later, but I will just add this strut for documentation's sake. d4.strut. Okay. There's a lot here, and there's a lot to explain. So where should I start? So in short, what is... Sorry, just had to make the stream public, because for some reason it was streaming as unlisted. Public. Okay, so what is ext4? ext4 is a file system. What is a file system? So you'll remember that something we looked at last time was what a tar.gz file looks like. If you look at this gz file, you can see that it's a list of records. Record after record after record after record. In between each of these records is the contents of the files inside of them. You can sort of think of tar like a file system. In fact, the Linux kernel can boot up with an IntRamFS with CPIO, as we did last time. That's similar to a file system, but the key difference with a real file system like ext4 is it's designed to effectively handle lots of mutations happening to the data as things happen to it on disk. So the file system starts off by being formatted and empty, and then you can very efficiently add to a file system over time. To format a file system, you only need a few very basic structures, but then gradually you can add more and more things onto the file system over time. File systems can also store a pretty varied collection of file metadata inside of them, and they are generally designed for a high degree of resiliency, something which tar is not. Random bytes get corrupted in a tar file, it's likely that that file is going to be unusable. Random bytes get corrupted on your disk, maybe you'll lose 1 or 2 files, but if that, there are ways to prevent. So file systems are incredibly resilient to faults and issues with them. How is this implemented from a internal structure standpoint? So ext4, using ext4 as an example here, ext4 starts off with the idea of superblocks. Superblock is the structure pretty much at the start of the disk that contains all the information about what the file system is. There are multiple backups of the superblock located elsewhere on disk. Spoiler, TinyRange does not care about that, they're not necessary, but the superblock gives you all the basic information. It tells you how many inodes are in the file system. An inode is a single record of a file or directory in the file system. Tells you how many blocks there are. File systems are not byte addressable, they are addressed by blocks. So you can think of the entire file system as a big giant virtual memory map consisting of all of the different blocks that make up the file system. Some blocks are used for some purpose, some blocks are used for other purpose. If we look at this local Alpine rootfs, there will be a series of blocks that contain that file contents. Full disclosure, my host machine is running BTRFS, not ext4, so I won't really be able to give a good example of that. But yeah. We also have the number of reserved blocks, we have the number of free blocks, we have the number of free inodes, we have the location of the first data block, the block size, the allocation cluster size, blocks per group, clusters per group, inodes per group. ext4 has a superblock at the start, and then the rest of the file system is organized into a series of block groups. Each block group contains its own list of inodes inside of them. Remember, an inode contains a file directory metadata, and it also contains bitmaps that tell whether a particular inode's been allocated, whether a particular block has been allocated, and the block groups contain header information for this as well. You can think of it as a multi-tiered thing, where at the highest level there is the superblock that consists of the entire file system. The next step down is all of the block groups, and then the next step down is the individual inodes and blocks within that block group, of which the inode table and bitmaps consume some of the blocks in those block groups as well. Besides that, there's a bunch of miscellaneous record keeping here. The only really important things is what features the file system supports. For a lot of people who are running Linux computers, you're probably using an ext4 file system, unless you're running in some kind of specialized server or other thing like that. You're probably running ext4, and ext4 has a lot of optional features and little capability associated with it. It has journaling. Journaling is not important and is outside of the scope of this discussion. That's all I'll say about journaling. It contains metadata checksums. Also not important, also out of the scope of this discussion. You're going to notice a pattern. It contains miscellaneous flags, it contains snapshots, it contains error tracking information. It contains user and group quotas. It contains encryption information. It contains what encoding a file name character set is. The thing is, ext4 and the file systems that it's based on have been around for decades and decades at this point. And the Linux kernel is both extremely resilient to changes in the ext4 format, well, is both extremely resilient to corruption and errors with a disk, so there's a lot about an ext4 file system that the Linux kernel doesn't strictly care about, and these file systems can be upgraded in place over time. If you had a tar file and you wanted to move it from one version of tar to another, theoretically, you would probably need to go through and rewrite that entire file again. If you have an 8 terabyte file system, even on a really fast SSD, that is going to take absolutely ages. And it's also not going to be good for the disk either. So file systems are designed to be incrementally advanced over time. The minimum set of capability that you can implement in an ext4 file system is actually not that much. All of this complexity associated with a file system, all of these features are what makes writing a modern file system driver so complicated. Because if you take a real file system from a real computer, it will be using a lot of these different features. It will have them enabled in one way or another. There's a lot of different code parts that need to be implemented. Maybe you'll have some legacy ordered directories. Maybe you'll have all kinds of weird content associated with them. But if we're writing the code ourselves to format and create the file system from scratch, as it turns out, we don't need nearly that much information. Which is why my ext4 file system driver, while being completely compatible with the Linux kernel, is written in a relatively small amount of Go code. The core ext4 parts that are specific to ext4, the parts that I've written for it, they're like 2,000 lines of code-ish. There's a bit of other library code around that it uses, but the core's like, 2,000 lines of code? It's not that much. And we can expose this file system to a virtual machine using network block device. Network block device is... So a hard drive is read in terms of blocks. The file system is organized in blocks. Hard drives are organized in blocks. You can do reads and writes of arbitrary blocks at arbitrary locations. All NBD is it's a common protocol that turns a hard drive into a network service. You could theoretically have a hard drive that exposed that kind of API directly, and systems could use it. That kind of thing you can sometimes see in enterprise with things like NVMe over fabrics and iSCSI type interfaces, but in this case we're just using on a local system. Qum supports this directly without any involvement from the guest kernel. So we're going to be using VirtIO block just because it's fast. We could expose this file system to the virtual machine over an IDE interface. And right now, we've just got ext4 code. There's a fair amount of code associated with it. But in the future, we could add FAT, we could add NTFS, we could add any other kinds of file systems. So, the next thing to be aware of, this generated code is code generated from this ext4 structure. Why is that? Because the core of the file system implementation that we're going to be doing today is the idea of treating a file system as if it's some mappable section of virtual memory. And we're exposing that virtual memory space into the virtual machine as a block device. So we're going to be mapping different pages. We're going to be thinking of the file system at a low level as a series of pages occupying space in memory. And as part of that, we want to be able to treat everything as a byte, everything as a directly addressable byte structure. So if you're relatively familiar with Go, you'll know that there is a number of different types of IO.reader, IO.writer, a variety of different IO interfaces. And you'll recognize these two hopefully, which is IO.readerAt and IO.writerat. These are just read and write methods that take an offset. And you can see it's pretty simple. We can read from these structures just by looking at a by offset. All the code generation behind this has done is it has taken something that's ordinarily a regular structure that looks very much like the underlying C structs that would have constructed this, and it turns it into the code implementing that directly. So instead of being a structure in Golang, we've created our own structure abstraction that thinks of all of these as fixed size byte arrays. And the fact that these byte arrays are fixed size means that the compiler doesn't have to include bounds checks into this. So the compiler can know all of these accesses are safe. So from the compiler's perspective, this superblock structure looks a lot like if we had implemented this structure in regular Golang code. And that's more or less what the code compiles down to. So this is the generated code. These are the ext4 structures. The next file from this is ext4.go. It's 2,000 lines of code. We're going to have to make a fair few changes to this, since it is using my old file system logic. So we're going to have to go through and fix a whole lot of these things. So we also need VM. We're going to make vm.go, package VM, and we are going to grab this and make sure that we import TinyRange pkg file system VM. And we're going to search for log dot and replace this with best log. The old version of TinyRange uses its own custom logging library. I may introduce something like that in the future. Not sure yet. So slog.warn, slog.warn. Actually, no, I'll just go through these manually. It won't take too long. There's also a bit of code to read ext4 file systems that I'm not sure if I cut out of this already. If not, I will cut that out shortly. And in fact, yeah, it is that bit of code just there. So I will remove the reading support. slog.info, slog.debug, save, log. I think I just forgot one or two things. Let's try to import that thing that doesn't exist. Yes, I did forget some. Cool. Has that removed that? Yes, it has. Right, I would really like this to stop complaining at things so loudly. Right, come on, tidy. Was that all that was needed? Oh, guess so. Right. Cool. And now I just have all of the VM code as well. Although I'll remove that read support. The read support is something I only used initially as I was testing it out, and I think I'm going to introduce something like read support in the future. But I am definitely going to make it from scratch. And I will let the rest of the code get cut out once I figure out what code's needed and what code's not needed. So in VM, we have this. We have this whole bit of code. Instead of log dot, we will turn this into slog dot. And then we have a common.go. We have file.go. Fragmented.go. Offset.go. Padded.go. Raw.go. Truncated.go. And finally, bitmap.go. And I think fragmented.go was the only one that used logging. Cool. So this should now hopefully stop complaining. Oh, and array.go. Right. So now we have this whole ext4 structure. And I'm just missing this basic set of utilities that CodeGen used. Cool. Well, that compiles. And now we can see what code is unused. Extent tree 1, map extent tree is not needed. Extent tree 1 is eventually going to be used, but not yet. Map linear directory is not needed. And then there are all these different flags. Map hash directory is not needed. There we go, reduced down to how much code did we add here? Oh, we went from about 2,000 lines up to 5,000 lines. That's fair. And I could probably, this could probably do with a bit of cleanup. This code was hard won. There's a lot of little details and changes within this, and you'll see comments of how to handle handle various different edge cases. But let's explain how this works. So we have ext4, and its top level item is create ext4 file system. It takes a VM, which is a vm.virtual memory. You can think of virtual memory as a page table for a particular region of RAM. Virtual memory itself supports a io.reader_at and io.writer_at interface. So you can read arbitrary locations within a block of virtual memory. You can write arbitrary locations within a block of virtual memory. The ext4 code uses the memory mapping capabilities within the virtual memory class, or within the virtual memory structure, and it takes offset and a size. Offset is the offset into the virtual memory, and size is the total size of the file system, since we need that to calculate a lot of the core statistics about it. A lot of these numbers are just hard coded, observed from regular ext4 file systems. Things like the magic number, the number of reserved blocks, the maximum mount count, the inode size, the state and errors, various other information like that. We randomly generate a UUID, and we also of course set a series of feature flags on the file system. One of the really cool tricks that this code can do, which is super interesting, is it can make the entire file system deterministic. You can take some kind of structure, write it into this file system, and create repeatedly byte for byte identical ext4 file system that can be booted up on a Linux system every single time. And that's kind of a bit awesome, in my opinion at least. The file system could do things like dumping information and metadata about it, and it implements all of the basic kinds of facilities you would expect a file system to do, with the core difference that this file system is not read-write, it's write-only. The whole file system is designed around the idea that all of the content is going to be written to the file system, and then it's going to be used. So that means that compared to a regular ext4 file system that you may be using with your own computer, because we don't have to worry about deleted files, our file system never gets fragmented, which is why the code to do this is so simple. As it turns out, this works very well. We can support ext4 file systems nearly as big as we want, but right now there is a limitation where we only support files up to 512 megabytes in size. And the reason for that limitation is we're using Extentree 2 instead of Extentree 1, because Extentree 1 needs more work. Extentree 1 is essentially a little hack that statically allocates a single Extentree node. The Extentree is a structure that points to the location of data on disk. We just allocate a single one of these with 4 nodes inside of it, which means we can only consume up to this particular number of blocks within a file. And unfortunately, that limits, because individual block groups only contain 128 megabytes of blocks, that limits us to about 512 megabytes as a maximum file size. As it turns out, for a lot of cases, that's not really a big problem. Something I would definitely like to address in the future, but right now, it's okay. So that's how this ext4 code works for the most part. It's a lot of relatively simple accounting and making changes to all of those different data structures and organizing things around on disk. What makes it all possible is the virtual memory code behind it. And like I said, this just implements essentially the same kind of memory mapping that an operating system uses, which is organized in terms of memory pages. Except, unlike, I could theoretically use the operating system memory mapping functionality to do this. I could just allocate a large contiguous chunk of memory, and then make that directly available to a virtual machine as a NBD block device. The code to do that would be very simple. It would be extremely performant because operating systems are really good at memory mapping, but you'd lose a little bit of flexibility in it. The reason this code is so complicated is probably because this one file here, fragmented.go. Fragmented allows you to map arbitrarily small fragments of memory with whatever custom class you like behind them. You can create a 1-byte allocation and have a custom behavior every time that block is read or written to, which is kind of useful as you're going through doing the development of this. But also, this fragmented code is probably the main source of performance issues in the system right now. So, we now have the ext4 file system code, released on the same license as the rest of the code, Apache 2. Let's actually use it. So if we look in the code right now, when we go to create a virtual machine, let's just do a test of this effectively first. Let's take our tar.gz, which is the Alpine code, and we will turn that into an ext4 file system. So we will create a new command called makefs, and we'll just have a main.go. Package makefs. This will take a series of tar.gz files and turn them into an ext4 file system, which we can write to disk. It's a lovely little tool. Also, remember, all of this code, because it's in pure Go and doesn't rely on any other libraries, this will work in every operating system Go supports the exact same way. The ext4 code itself does not depend on any third-party libraries, except I think like a UUID generation library. Yeah, UUID generation library and some type parameter constraints. That's it. So, if you want to make an ext4 file system from a series of tar archives on Windows, once this code is open sourced, you'll be able to. Easy as that. So, vm.new virtual memory. So, firstly, we'll just set the page size to 4096. And we'll set the total size to size equals flag dot int. We'll default the file system to 64 megabytes. And we'll also make this in megabytes. Size 4 times 1024, and this will be an int right now, so we'll have to cast this to an int 64. And then output equals flag.string. Input file to write the file system to. And flag.parse. This is create a virtual memory. fs is ext4.create ext4 file system. Pass the virtual memory, offset at 0, and it's size times 124 times 1024. And this can sometimes return an error, and we will do a nice wrapper for this. And so we'll just call makefs main. This also has to be an int64. And these file systems don't have to be closed or anything, so we can just do underscore equals fs, and then we can just do out error equals os.create output if error is not null, error defer output close. Copy, destination is output, and source is io.newSectionReader VM. I'll set it 0, and I'll just fs size is that, size, fs size, and fs size. Error is not equal to nil, return error. Otherwise return nil. Go run, cmd, I'll just say flag dot package name. Now it's used. Good. If star output is equal to empty string, then flag.usage error f output must be specified. Go run cmd, go run, just check out what this is. Go run github.com/tinyrange/cmd/makefs. And dash output local fs.img. The fs.img, just fix that, and file fs.img. Look, it's a file system. And if we do fsck.ext4 dash force check fs.img, so some of the parts of the file system have an invalid mode. Okay, so the trick that I normally use with this is to diff two file systems and see what they changed. CPFS and FSCK ext4 -f fs.img-h. Answer yes to all questions, and their block inode looks invalid. So xxd fs.img output fs out.txt xxd fs to fs txt and diff fs original img and fs original out. That's fs. All right, we can see that surprisingly few changes were made to it. This I believe is the information about the file system being checked and the time that the file system was checked, and we can see that the only things that were modified here were the actually I should flip this to over. We can see that the only things that were modified there is the time, so that's in the super block. Yeah, so the super block was slightly modified to add updated times, just those two, and then probably it's exactly what the tool said that happened. FSCK, which is just that the bad block inode looks invalid. The undelete directory has invalid mode. And yeah, 6, 7, 9, and 10. And we can see those modifications. There's an EDO1. There's an EDO1 there that was just cleared for all of them. So let's just go over to the code and see where that modification was made. ext4 has a series of reserved inodes, which is what it's complaining about there. And this is going to be this fs.allocate inode part here. So it updates so it calls block group.allocate inode, and if so, it sets a default wrapper to it. So we are probably going to have to set the mode of these inodes manually to 0. Inode else inode dot node dot set mode 0. Simple as that. I actually remember making the modification to the code, setting default modes because some parts of the file system couldn't be read or written, and that was causing bugs at a user level. But the Linux kernel won't complain about that. This is just fixing a bug for complete mistake. So if we now run fsck, we can see that the file system that we created is completely correct. Amazing. Right, we are now generating valid ext4 file systems. So let's put some files inside of them. So all this will do is it'll go for in range flag.args extract archive to from into fs. I'm going to make this a slightly general tool, just because I think it'd be a useful thing to have in general. This code is Apache 2 licensed. You can take the ext4 file system code and use it in other Go projects as well. That note that I said earlier about being able to make the file systems deterministic, if for some reason you're trying to generate like virtual machine disk images and you want them to be completely deterministic in the generation and fully reproducible, this would be a great place to start with that. Because I believe that the regular ext4 file system tools that are officially used with Linux systems don't support that feature, but this code does. Input string fs star ext4.ext4 file system. This returns an error. If strings dot, this code is just going to look for suffixes, but reader if input if strings has suffix input dot gz, then reader gzip dot new reader. Okay, f arrow equals os dot open input. If arrow is not to nil, turn nil error. Turn error for f dot close. So we're just going through each of these archives and extracting them into the root of the file system. So this is going to take f, and that's already works. So input equals strings dot string suffix input dot gz, and then if strings dot has suffix output, input put dot tar, else turn input as a non-archive format, and tar reader tar dot new reader else reader equals f. For header is tar reader dot next. I believe we wrote this exact same code in a previous stream. I will just go and copy paste that code quickly, since it's not worth writing again. I believe that was step 2. Yeah, this was the CPOS. The code is honestly different enough that we don't need to copy it. simply because the interface for dealing with CPIO archives and the interface for dealing with a ext4 file system just ends up being different enough anyway. Then turn nil, switch header dot type flag, case type reg, case type symlink, case type dir, and default. And fs dot create file. So contents error is io.real from the tar reader. If error is not equal to nil, to error, and then fs dot create file. File name is header.name, and the contents is just a raw region. Choose the contents. Note that instead of being a raw region, that can be any interface that implements those methods. So normally as a optimization, instead of reading all of the contents of things into memory, I will use tar archives that are already being decompressed on disk and just use those instead. Then your memory consumption drops massively because reading from the file system inside the Linux VM translates into another read of the file system inside the host. So we only need to keep in memory the actual tar structures themselves, and even that it's sparse. So for a terabyte file system, you only need, I think, like a few hundred megabytes of metadata. So even comparatively small amounts of memory don't consume much resources with this system. So the file system also has optimizations to make it a bit easier. The file system also has optimizations to make sure that if you're reading multiple files, one after another, it will not do the full relookup in the file system again. So this is going to be header.linkname, and this is just going to be fs.makedir. Just takes the name and all refers to whether to automatically create parent directories as well. I don't think that will be needed. So, and then we just do is fs.chmod. File name is header.name. Mode is info is header.fileinfo. Info.mode. chown and ch times. Header.name, header.gid, header.gid. And finally, header.modtime. I only expose the modtime. So let's just run this code again and say entry dot already exists. So that means they probably have string prefixes. Header. If not fs dot exists input. header.name. Also I'll make name is path.clean header.name. Instead of using header.name, I will use the clean path instead. There we go. So if we look in local, rm, let's just delete all of these and recreate. So you'll see that all of this takes surprisingly little time. It's very efficient. And now we have fs.img. If we jump into a TinyRange VM where we can mount fs.img, we can see that it can be mounted. So I'm just going to do mount txt4 fs.img mount. If we look in mount, we will see, voila, we have a file system. In fact, we can chroot into here and log in, and voila, we just made a file system that is a valid rootfs. We just converted a tar.gz file into a Linux file system that can be mounted without any complaints or errors at all by the Linux kernel. It can read and write to it as much as it pleases. We can echo hello to world. We can cat world. We can do whatever we want. So with this relatively simple code, we have been able to create a full ext4 file system. Those numbers are going to annoy me if I don't fix this before it's committed, so I'll fix them now. So, yeah, we can create an ext4 file system. We have also proven that once we create said ext4 file system, we are actually able to use it inside of Virch. We are able to use it inside of a regular Linux machine. In this case, we used it inside of TinyRange, but there's would be nothing stopping me from mounting it on my host system. And yeah, let's now boot. Let's now boot from this file system. The code that we're going to use is basically exactly the same as this. Why do you think I wrote all this code in the first place? So let's actually because I don't want to duplicate this kind of code too much, I'm just going to make this be an extract archive to thing, and it's just going to look like this for now. So this code is very simple. It just does file system dot extract archive to, and yeah, right now it's very limited. Extract big file systems if you want. Or extract big tar archives if you want. Extract multiple tar archives into a file system. Spoiler, if you get all of the layers of a Docker image, and if you extract all of those layer tar.gz files into this file system, you can boot this up inside of a Linux VM. How do you think this is pretty much what step 6 is going to look like? And all that we're going to be going from step 5 to step 6 is, instead of step 6 is not going to be tonight, step 6 is going to be some other time, but all that we're going to go from step 5 to step 6 is replace this hard-coded tar.gz file that we're using with an OCI image. So what we're going to do here is So let's just, as a first brief step, see what happens if we boot this virtual machine using a tar that using this that we've written to disk. So let's go back into the TinyRange main code. We don't need the packet capture code right now. This is still a huge hack, but and we also gonna have a this image string. This image, disk image. Also just going to pull this just because I actually ended up updating this README with links to things. So we are going to cut those from there and paste those up there. 5, 6, 7, 8, 9. You can. I also decide to put the videos, since these videos turn out to actually be pretty interesting documentation for how all of this is done. So we have also got a disk image string. So the disk image is going to be if name equals disk image and start.string disk image. Oh, you may notice that we forgot to keep those attribute names up to date. They don't technically have to match, but it helps from a. It gives you nicer error messages if they do, and you can do all of this attribute mapping completely dynamically if you want to. So be fancy, get this all working. And there we go. And more or less all we're going to do is we are going to, in this TinyRange code here, we are going to create it. It's going to be 64 megabytes in size. VMem. So this is going to be package file system VM. Okay, now we're just going to do file system extract archive2. Input is just going to be this hard-coded path. Just move that, and we're going to extract it into this file system. If error is 1 to nil, error var out error equals out equals create local disk image if error is nil error. So what we're doing as a first step here is we are writing the disk image out to the system locally, which we will boot the VM up with that disk image, and then after that's done, we will switch it over to using NBD, because as it turns out in Cube, you can just pass NBD URL instead of a disk image name, so we actually won't have to change the hypervisor code once we've written this. Okay. So that'll create the file system. That'll create the file system automatically. And then all we have to do is modify cum.star. As I quickly look to see how my cum.star over here works. File equals dot format ctx.disk. IF equals IO. Read only equals off. And format equals raw. And go run github.com TinyRange/cmd/. All right. Apparently the networking code that we wrote last time has now broken. Oh, because creating the file system will take some time, and right now we're just hard coding in 100 millisecond wait. So this is why I said that's a hack. So in actual fact, we will want to do that earlier. So file system VM and file system. Hello world, we've got networking. So we will also just want to add support for mounting and executing the file system. Luckily, we can just get the kernel to do that for us. That only works if we are I guess we are no longer booting from an MFS. So I'll just specify that as empty string. And when we create the file system, we will also so that means we will no longer use this create root file system code, and we'll just do fs.create file. File name is int, and vmem dot the fact that it's called vmem. I'm just going to avoid confusion here and call this virtual machine. Makes it easier. Which means this can go back to just being vm dot it's getting the wrong VM. File system vm dot new file region, I believe, is the one. Just takes a file. F error. Init exe os.open. Init exe dot close. Now let's start open up. Let's build. We want this executable just here. Because the vm.new file region can take an init executable directly. Region. Error. Nil. Return error. fs.chmod. Int. And change the mode to fs.file. File mode 0755. Go fs. Go fs, not my regular fs. And I guess we don't need that code right now. We will need it in the future. The kernel that we're currently booting is a special TinyRange kernel that includes ext4 file system drivers and all that baked straight into it. Most kernels are not like that, so you do have to boot them up from an ramfs. In this case, for simplicity's sake, we're just going to be booting the ramfs directly. So, and I do actually need the other virtual machine. Package. I'll just call this virtual machine. No, I'm already using that name. Seems like so much. At least adds a little bit of clarity to know that I'm talking about virtual memory versus virtual machine. Error is nil, error. Return error. File region, create the file. Chmod int, and then we will also create init.star, which is just going to instead of being init region, it's just going to be raw region init script, and we will also make sure to check chown as well, or chmod. These functions can technically return errors, although I don't think this should be possible, but just for cleanliness sake, let's not ignore the errors. There we go. Failed to open error reading intRd. Oh, yep, because we're still including the intRd right now. Let's just remove that for now. Okay. That drive is apparently being called VDA. Oh, that's because I completely forgot some important parameters. Root equals dev VDA, RW, and init equals /init. There we go. Hello world. This is actually coming from the ext4 file system that we are writing. So what we can do with this is we can modify our init.star to just create an exec call. bin just create a run, which just runs a command. Bin login dash f root. And then if we go back into our init code and we add a globals run equals starlark new built-in run. This will just run a subcommand. For command args, which is an array of strings for arg args strk starlark string arg. I think we did this exact same code in the VM code. No, we actually used an iterator for that. If not okay, return none. String dot that's dot and cmd exec dot command is cmd args 0 cmd args colon dot and then cmd.std out equals os.std out stood out stood error and stood in stood out stood error stood in if error cmd.run no. Undefined run. Build.sh. Build TinyRange. Need to make sure this is rebuilt. Voila! Except instead of being an int ramfs, out t proc one proc df. Instead of being an int ramfs, this is now an actual proper root file system. And you can also see that the kernel is conveniently mounting dev for us already. So some things are going to work. We still have more file systems that we need to mount to get this to work in general, but we have now got the system booting an ext4 file system. Yay! And pretty much the last step before we have number 5 complete is to switch this from being just local disk.image to I believe it's just nbd:// nbd:// plus and then whatever the nbd server is. And now I will just remember what that code is to do that. Yes, I had some third-party code. CP. Sometimes I need to vendor dependencies and make small changes to them if they are randomly broke for some reason. So what I've just brought in here is the Go NVD server. I'm no longer using my logging thing. It's also under Apache 2, and it's this project right here. It's very cool. I want to use slog instead of log. The reason I had to do this was because the NVD code was missing some little errors with it. Now that the code's probably going to be open source, it's going to be worth contributing that upstream, perhaps. So, yeah. Wait for Visual Studio Code to figure out what it thinks the errors are. Plus equal. And instead of, because this uses the net stack abstractions, net dot listen. And I will just let it automatically choose a TCP port for this to listen on. And I do need to set up one of those backends, which is this bit of code just here. Init function doesn't need to exist. And then backend VM backend VM is VNet. And yeah. And instead of using TinyRange logging, which is called log module, because TinyRange, the original project, has existed for like 2 years, which predates the existence of slog in Go. So plus equal listener dot address dot string. NBD. And also we no longer have to write up the file. Voila! This is the virtual machine. This is the virtual machine booting up. using network block device. So if I rm the old local disk image, you can see that we're not creating any files on the host file system. We are, well, at local fs image is one we created earlier when we were doing the testing. But yeah, this is network block device code. We can extract an archive. We can extract an archive into this. Our OCI image code will likely work very similarly to this. We can open. We add our int executable inside of this. We add our init script inside of this as well, and then we simply send through a network block device. The network block device itself is very simple. All we need is Qum to do it, and yeah, now we no longer need an IntRamFS. We'll use the IntRamFS code later for actually handling kernels that do not support directly booting like that, which is most kernels. But yeah, on the to-do list is to do me fix this horrible hack. But yeah, I am gonna be a good person and add a little bit of documentation for how people may want to actually get this set up. Getting started. Build.sh. So the only thing that we'll need is local and cd local and wget our kernel build that we are currently using. Which is, at this point, quite an outdated kernel. I've been meaning to update it, but yeah. And we don't need the rms.cpr. Oh, we also need the rootfs that we're using. Cd local wget 2 releases. And yeah, if you run this code inside, if you add this code to a virtual machine and then run this code there, it should work. In fact, I am going to see if I can demonstrate that live. So we've added a whole bunch of code. CLOC is, yeah, we've gone from like 1,000 or 2,000 lines of code to 5,500 lines of code. Certainly add a lot of stuff. Commit -m step 5. And now this is publicly available. I will just grab the link to the current code on here. And let's see if we can replicate this inside of a TinyRange VM. TinyRange login. So my machine has distant virtualization enabled, but the kernel that we use by default, and which TinyRange normally uses as well, it doesn't support KVM. So we need to use different kernel, and that kernel definitely requires the specialized boot up. So alpha.tar.gz. And I will also make sure that this VM has Go installed. Tar, xf, and I will need to give it internet access as well. Okay, add bash wget qmu system x8664 or probe kvm intel ls dev kvm. Oh, now we have kvm. We can do build.sh. That'll download the right version of Go, which we don't have enough space for anymore. You'll notice one of the big benefits of TinyRange is that, and this is the network caching layer that we're going to be working on a bit later. One of the big benefits is once we do this at subsequent time, it'll go quick fast. My internet connection here is not that fast. It's fast, but it's not that fast. Because this is just coming from my local system instead. TinyRange caches all the stuff in the background. And the -- internet is step 10. Add support for connecting to arbitrary websites in the guest. Since our build instructions that we specified assume that you can and apk add curl ca certificates. And we'll just let this stuff build. I still need to download those few files. The reason those files failed to download is because the network caching layer does HTTPS interception. And TinyRange does put a file in the correct place such that when certificates are regenerated, they will automatically, the TinyRange certificate will automatically be added. Just a sec. When the certificates are regenerated, they will be automatically fixed, but that only happens when the certificates are regenerated, which they're not by default. So we will just make sure both of those are added, and we will do /build/TinyRange. Or probe kvm intel. There we go. Demonstrated that it's just as easy for you at home to get started and run a virtual machine with basic networking. You should be able to ping .10.42.0.1. Yes, you can ping it. You can't really do much more interesting with that. Also, for some reason, pressing Control-C terminated the entire guest. No problem. We can just start up another one. That's how fast those startups happen. Yeah, Kim's not catching the Control-C. That's step 8. Switch from using stood out from Cum to SSH from the host. Because we're currently just looking on a serial port. Not ideal. SSH from the host is a lot more stable, and also means that we don't get that big bunch of output as the system is starting up. We can still get that later on. We just have to do dmessage like that instead. But yeah, demonstrated. Easy as that to get set up. And this has only been an hour and a half long stream. Seeing that I have a pretty early workshop tomorrow, I will head to bed now. That was really good. Awesome. Making sure that all of that's committed. It is. Right. Thanks for watching.